The other day I went to the mall and it was fairly noisy inside. People were walking, people were talking, and there was actually background music playing. So I went to try this Bose noise cancelling headphones, and when I put it on, I was blown away. I was like,
oh my god! Wow! Oh my god!
how did engineers manage to reduce the noise to almost zero? Well, in this video, that's what I wanted to talk about. I know some of you probably own noise cancelling headphones and are like, well, this is nothing new, but do you know how it actually works? So yeah. Now, what is sound? The best way I can explain sound is when something vibrates air molecules such that it causes them to compress and expand, compress and expand, compress and expand, and it travels like that through the air until it reaches our ears or a microphone or something. You can also visualize it as like a sine wave, something like that, a sine curve, or you can just think of it as compressions and rarefactions through the air. But generally, that's how sound travels through the air. How does humans hear? Well, these same compressions and rarefactions, the sine wave, they hit your ear and they vibrate little tiny hairs in your ear canal. And these hairs vibrate at different frequencies, and depending on the frequencies, your brain interprets that as sound. And it's actually very similar to how a mic works. Wait, let me do a fact check on that. Yeah, so when sound hits a microphone, it has a little diaphragm in it. So when the sound hits the microphone, it vibrates that little diaphragm, and then that converts the sound wave into electrical signals, which is important for what I'm gonna explain later in this video. So humans can hear up to 20,000 hertz and as low as 20 hertz, with the lower end being the nice punchy bass and the higher end being the highest. Sound travels at approximately 740 meters per second in dry air and at sea level. So how does active noise cancelling headphones work? So basically, when you put on your headphones, the mic on the headphone listens for background noise, then it converts it into electrical signals, and then it inverts them, meaning that it converts the negative half of the signal to positive and the positive half of the signal to negative. It then plays this through the headphones, the speakers of the headphones. So essentially what happens is that you have equal and opposite signals coming together and they cancel out, you know, just like how two opposing forces, equal and opposite, they interact and they cancel each other out. It's pretty much the same for waves. So that's basically how active noise cancellation works, and it actually has a name. It's called destructive interference, and if you take physics, then you should probably know this. It is important to note, however, that noise is never really truly cancelled out. That's why engineers prefer to use the term active noise reduction instead of cancellation, because due to the limitations of the headphones and other factors, the noise is never truly cancelled out. But you know, for marketing purposes, active noise cancellation is used instead. This is a circuit of a noise cancelling device that I drew here, and I know it looks kind of intimidating, but we can break this circuit down into 3 different sections. The sections here are denoted by these red dashed lines, and here we have the pre-amplification stage. This section here, this is the all pass or delay stage, and the last section here, this is the summing amplification stage. And here at the beginning we have the mic, where that listens for background noise and converts it into electrical signals, and the end here we have this headphone or the speaker, where it outputs the inverted signal so that it can interact with the original noise sound wave. So in the beginning we have the input where the mic is. If you put on your If you own a pair of noise cancelling headphones, you will notice a small hole on your on your headset, this is probably the mic which listens for background noises. Now when it picks up background noises, it converts it into electrical signals where it then goes to the pre-amplification stage. And what this section basically does is pretty much what the name implies. It amplifies the noise signals, because these background noises, they produce very small voltages in the circuit, which can be quite hard to handle. So it is important that this be able to amplify the noise signal. Now the magnitude in which it amplifies the signal is known as the gain, or AV, as I wrote here. And this is simply a ratio of two resistors, namely R1 and R2. So let's say R1 is 100 ohms and R2 is 10 ohms. That would give you 10. So then the amplified signal is equal to the gain times the input signal. This means that the gain, which is 10, times the input signal, which just came in from the mic, will be multiplied by a factor of 10. And that would give you your output signal. So in other words, we can control just how much the input signal is amplified by adjusting the values of these two resistors. So the next part of this circuit is the all pass or delay stage. Now you might be thinking, why do we need to delay the signal? Well, remember I told you that sound travels at approximately 740 meters per second in dry air at sea level, and electrical signals essentially travel at the speed of light, which is 300 million meters per second. So imagine if we didn't have this part of the circuit here. What would happen is that the sound from this circuit would reach your ear before the sound from the environment, from the background, and we don't want that to happen, because then you wouldn't get any noise cancellation at all. Remember, for noise cancellation to occur, there needs to be destructive interference. That means that two equal and opposite waves need to come together and interact and cancel each other out. So we need to delay the signal coming from this circuit just a little bit so that it matches the speed that is coming from the speed of the sound that is coming from the outside. So the last part of this circuit here is the summing amplification stage, and it does pretty much exactly what the name says. It combines whatever music you're listening to with the noise signal that came in from through the mic, and it doesn't do any amplification, it just combines them really. But what it does do is that it reduces the amplification of the noise signal back to the original, because remember, in the pre-amplification stage we needed to amplify the signal to a higher level so that the circuit can better handle the voltage. So now in the last stage we're bringing it back down to its original voltage and output it through the headphones so that it can properly match with the ambient background noise. And this can be done with the help of a potentiometer, so that we can adjust the resistance values so that it matches the noise signal that is coming from outside in order to achieve the proper noise cancellation effect. The last part of this circuit here is the power supply filter. It is not really needed, but it is good to have for several reasons. The capacitors from C5 to C7 along with R11 act as a low pass filter, meaning that it blocks higher frequency signals from passing, but it allows low frequency signals to pass into the circuit. It would be an added benefit to have high frequency signals be removed from the circuit. This is because a phenomenon known as aliasing might occur, which is when the circuit has problems identifying the frequency of a signal and causes distortions in the sound. It is also worth noting that not all noise cancelling devices use this exact design. Some of them implement their own design to accomplish the same effect, but I just chose this design to show just how it actually works on an electronic scale, just to give you an idea of the different components to accomplish active noise cancellation. Active noise cancelling technologies are also being implemented in automobiles as well, where microphones are placed throughout the interiors of the car to listen for engine noises tire noises, wind noise, and then it plays an inverted signal through the car's stereo system and essentially canceling out all the background noise inside the car. Engine noises in particular are quite easy to cancel. That's because they are periodic and therefore more predictable, so they produce more repetitive waveforms that are easier to handle by circuits like the one I showed you just before. This is the reason why active noise cancelling technology is really effective in planes as well, because the engines in the airplanes are really repetitive. They produce really predictable and repetitive waveforms that are easier to cancel than just random noise. So in general, the more random the noise, the less easier it is to cancel, and the more repetitive it is, the easier it is to cancel. In general, active noise cancelling devices are more expensive than your passive noise cancelling devices. That's because there is more technology, more expensive electronics that goes into making these things happen in active noise cancellation. While with passive noise cancellation, well, I can literally just cover my ears, and that's a form of passive noise cancellation. That's pretty much it. I hope I gave you a little bit more insight as to how active noise cancelling technology works. And that circuit that I showed you before, you can actually build that, by yourself on a breadboard, and you can actually test it out to see if it works for yourself. So that's it, guys. I really hope you enjoyed this video. I try to keep these videos as short as possible. Please remember to like, share, and subscribe. I really appreciate your feedback, as it does help me improve the qualities of my video. Each video I bring out, the quality gets just a little bit better and better. So I am getting better and better with more practice, of course. So yeah, again, thank you for watching, and I'll see you next time.